In this video, I'm gonna be explaining this article, Jointly Multiple Event Extraction via Attention-Based Graph Information Aggregation. This paper in 2018 and is related to this literature review, and so this article cites the article that I'm gonna be explaining. And this article is also very interesting. It uses contrastive pre-training for event extraction. So event extraction is of practical utility in natural language processing. In the real world, it is a common phenomenon that multiple events existing in the same sentence where extracting them are more difficult than extracting a single event. So multiple events is more difficult than single event. Previous works in modeling the associations between the event by sequential modeling methods suffer a lot from the low efficiency in capturing long-range dependencies. So we propose a novel jointly multiple event extraction framework to jointly extract multiple event triggers and argument by introducing these syntactic shortcut arcs to enhance information flow and attention-based graph convolutional networks to model graph information. So this is an example of dependency parsing that you can use Stanford Core NLP to get it for free. So there are two events in the sentence, a die event which is triggered by the killed, and so the approach is that we extract events in the sentence for three reasons. Firstly, in our investigation, we find that the document level co-occurrence distribution of 33 types of events in ACE are relatively similar to the sentence level co-occurrence distributions. So in figure 2, for example, the blue bars and the orange bars indicate the conditional probability distribution of all 33 event types in the sentence and the documents. So W is a sentence of length n. We have n tokens. And so we have k events, and k is the number of entity mentions. So we have these entity mentions, and our framework consists of the following modules. First, word representation. Then we have syntactic graph convolutional networks, like many previous papers that I've explained. Third one is self-attention trigger classification. And finally, argument classification that predicts the roles each entity mention plays in the event candidates of specific types. So for word embedding, you can use GLOV for part of speech. You can use also part of speech because we are concatenating these things. Also, the positional embedding is a good feature because if WC is the current word, we encode the relative distance, and the entity type label. So similarly to the part of speech tagging label embedding, we annotate the entity mentions in a sentence using begin, internal, and outside annotation schema. So this is the architecture. We give these dependency. We create a graph convolutional network using this adjacency matrix that is obtained by dependency parse, and then we do argument row and trigger classification. So here we update the graph convolutional networks. Everything is standard, but to reduce the number of the parameter numbers, we modify the definition of type label. So the new K only have 3 type labels. And we calculate a weight for each edge as well. So with this additional gating mechanism, this is the final syntactic graph convolutional networks. So as stacking k layers of graph convolutional network can model information in k hops, and sometimes the length of shortcut path between two triggers is less than k, so we miss it. To avoid information over propagating, we adapt highway units, which allow this information flowing across stacking layers. But instead of feeding the word representation into the first graph convolutional networks, we just use this by LSTM. It has a better contextual representation. And then we have this self-attention score and the context vector at position I. So here we feed the context vector C sub I into a fully connected network to predict trigger label, because we have begin, internal, outer annotation. And F here is just a nonlinear activation. Y sub T is the final output of the ith trigger label. And for each entity trigger pair, so this is a pair, we concatenate them, and then linearity, then nonlinearity, then we get the argument roles. But we minimize the joint negative likelihood due to data sparsity, because this data set AC, this is very popular, but it has data sparsity. We adapt our joint negative likelihood by adding just a biased item term. And this I is just the indicating function. So you see, we always do argument identification and argument role. Also trigger identification on trigger classification. You see state of the art, even this for this approach is less than 75%. So they introduced syntactic shortcut arcs to enhance information flow and adapt the graph convolutional network to capture the enhanced representation. Then a self-attention aggregation mechanism is applied to aggregate the associations between events. Besides, we jointly extract event triggers and arguments by optimizing a biased loss function due to imbalances in the dataset.